Students, we're going to be learning about equilibrium system, equilibrium system of a chemical reaction. Okay, by the end of this class, the student should be able to state the conditions for equilibrium. That means state the condition in which equilibrium occur. Two, derive the equilibrium constant K of a chemical reaction. You should be able to mathematically derive it. And then three, write out the equilibrium constant of a chemical reaction equation. Of course, we should be able to do this at the end of this lesson. Now, let's start with the definition of an equilibrium system. What is an equilibrium system, or what is an equilibrium reaction? A reaction is said to be in equilibrium when the rate of the forward reaction is equal to the rate of the backward reaction. That is when you say a reaction is at equilibrium system. Now, for example, let's take evaporation and condensation, which is a physical phenomenon that usually occurs. Now, evaporation and condensation can occur, of course, when the system is closed, in a closed system. It's possible that evaporation and condensation can occur simultaneously in a closed system. Now, when the rate of evaporation is equal to the rate of condensation, when the rate of evaporation is equal to the rate of condensation, you say the system is in equilibrium. When it is equal to, you say the system is in equilibrium. Now, but if or when the system is opened, of course, an equilibrium reaction cannot take place. Yes, because evaporation is going to be greater than condensation. That is, the rate of evaporation will become greater than the rate of condensation. So we say this system is not an equilibrium system, but this, of course, is an equilibrium system. Why? This, of course, is an equilibrium system because the rate of evaporation is equivalent to the rate of is equivalent to the rate of condensation. I come back again, the rate of evaporation is equal to the rate of condensation. You say yes, the system is in an equilibrium system. Okay, all right, the system is exhibiting equilibrium. Okay, now let's continue. Now, equilibrium equation formats. Now, how is an equilibrium equation format written? Now, this is a chemical equilibrium equation format should be written in this very format. Now, what sign is this? This sign represents the reversibility sign, of course, reversibility sign. And of course, it's made up of two half arrows. The arrow pointing forward direction represents the forward reaction. The arrow pointing the backward direction represents the backward reaction. Of course, the whole sign is what we regard to as reversibility sign. All right, conditions for equilibrium. What are the conditions in which equilibrium will occur? Although some of us already have this in mind already because I've shown you a little illustration at the beginning. Now, conditions for equilibrium. The conditions for equilibrium are one, and which is the most important. The reaction must occur in a closed system. The system has to be a closed one because equilibrium cannot occur in an open system. It is impossible for equilibrium to occur in an open system. It has to be closed. Then two, the reaction must be a reversible one because not all reactions are reversible reaction. Example is acid reacts with base to form salt and water. That reaction is not a reversible reaction. So it has to be a reversible one. For example, now if reactants A and B combines, if reactants A and B combines together, of course they form C and D. If the reaction is in a closed system, of course C and D can combine to give us back A and B. That is, C and D reacts to give us or to form A and B at the end of the day. So we say yes, of course, that this is an equilibrium system. Okay, a real life example is the composition of calcium carbonate. The composition of calcium carbonate. Calcium carbonate breaks down to produce calcium oxide and carbon 4 oxide gas. If the system is a closed system, the calcium oxide formed and carbon 4 oxide reacts to give you back your calcium carbonate reactant at the end of the day. Now, if the rate at which calcium carbonate is decomposing to give us CaO, which is calcium oxide, and CO2, which is carbon 4 oxide, is equal to the rate at which calcium oxide is combining with carbon 4 oxide to give us back the calcium carbonate, you say yes, this reaction is actually an equilibrium reaction. Of course, it has to occur in a closed system. All right, equilibrium constant. Of course, before we look at the equilibrium constant of a chemical reaction, quickly let's know see what mass of action states. The law of mass action states that at constant temperature, the rate of a reaction is proportional to the active masses of each of the reactant, which means what determines the rate of a particular reaction is the active masses, which it means the masses taking part in a chemical reaction, determines the rate of a chemical reaction. Now, imagine, of course, if we have A reacting with B to form a product, this reaction is occurring at a particular rate, let's say R, let's call it R. So how do we now deduce the rate of this reaction? Of course, the rate of this reaction is proportional to the active masses of A and B raised to power the mole of A and B, which is M and N in this case. Now, take note that for every proportionality sign, there must be a proportionality constant, which means R is equal to K A raised to power M times concentration of B raised to power N. Now, K is a constant. K is the reaction constant at this point. K is the reaction constant at this point. Okay, that is what it is. All right, now, mathematically, let us consider a system in equilibrium. Now, for example, imagine I have element A combining with B to give us C and D. Let's say we have M mole of A combining with N mole of B to form P mole of C and Q mole of D. It's also possible that C and D combines to give you back your reactant. Okay, let's call the fourth reaction R1. Let's say the fourth reaction has a rate. It's occurring at a rate. So let's label that rate as R1. And then the backward reaction is occurring at a rate. Let's label that rate R2. Okay. Now, you agree with me according to the law of mass action that R1 is proportional to its reactant, actually the concentration of its reactant. So, A raised to power M multiplied by B raised to power N. Of course, you agree with me on this case. Then, that means, technically speaking, for every proportionality set, there must be a proportionality constant, which means R1 is equal to K A raised to power M multiplied by B raised to power N. Okay, let's call this equation 1. Now, let's continue. Now, this time around, I want to look at the backward reaction. Okay, of course, let's call this K1, which is the constant of proportionality for reaction 1. Then R2, which is the rate backward reaction, is equal to K2 multiplied by concentration of this time around is the products that are actually reacting to give back the backward reaction. So which is concentration of C raised to the power P multiplied by concentration of D raised to the power Q, which is its mole coefficient. Now, that is what it is. Let's call this equation 2. But at equilibrium, you will agree with me that at equilibrium, forward reaction is equal to backward reaction, which means equation 1 is equal to equation 2. Technically speaking, it means when R1 is equal to R2, we'll now be having K1 A raised to power N, which is the equation for reaction 1, is equal to that of reaction 2, which is K2 D, concentration of D raised to power Q. Now, let's make K1 and 2 separate of the formula, which means we are going to divide both sides by this, which is A raised to power M times B raised to power N. By dividing both sides, it means I'm going to be getting K1 over K2, which will now be equal to K1 over K2, which will now be equal to C raised to the power P times D raised to the power Q over A raised to the power M times B, concentration of B raised to the power N. So, let's say let K1 and K to be, let's say K is equal to K1 over K2. Therefore, this equation becomes K equal to C raised to the power Q raised to the power P multiplied by D raised to the power Q divided by A raised to the power M times B raised to the power N. So technically speaking, it means, of course, what is K? K is the equilibrium constant when R1 and R2 are equal to one another, which means K is equal to the equilibrium constant. So that means to write an equilibrium, if you want to show an equilibrium expression for any chemical equation, all you need to do is write your K, which is stand for the equilibrium constant, equal to products, because C and D are products. So concentration of the products raised to the power the mole of the products, let's say P stand for the mole of the products, divided by concentration of reactants raised to the power the mole of the reactant. Let's say M represents the mole of the reactant. So that's just it. Just mole of product divided by mole of reactant. That is all it is. All right. Now let's progress. Okay, all right, let's progress. Now generally, we can see that the equilibrium constant of a reaction is given as K, which is concentration of product raised per mole of product, divided by concentration of reactant, or mole of reactant, raised per mole of reactant. Okay, then for example, write an equilibrium expression for hydrogen reacting with oxygen to form 2 moles of water. That's 2 moles of hydrogen reacting with a mole of oxygen molecule to form 2 moles of water molecule. All right, to write this equation, remember you have to follow the formula, and the formula is very simple. It says that K is concentration of product divided by concentration of reactant raised to power their individual moles. So, which means K is going to be equal to product here is water divided by reactants. What are the reactants? Hydrogen and oxygen, which is concentration of product raised to power the mole of product. Of course, the mole of water is 2 divided by concentration of the reactant, which is hydrogen raised to power 8 mole, which is 2, multiplied by concentration of oxygen raised to power 1. Of course, and that's what it is. So that is the equilibrium. So this now represents the equilibrium expression for water combining with, for hydrogen combining with oxygen to form water. This is the equilibrium expression for it. All right, let's look at an example. Now, here's an example. Show the equilibrium constant for the following reaction. What's the reaction? That's it. That's sulfur 4 oxide. 2 moles of sulfur 4 oxide combining with a mole of oxygen gas to give us 2 moles of sulfur 6 oxide. How do we now write the chemical, show the chemical expression, the equilibrium expression for this reaction? Okay, to do this, you have to follow the formula I gave you, which is equilibrium constant is equal to concentration of product raised to power the mole of product divided by concentration of reactant raised to power the mole of the reactant. So what is the product in this case? The product is this. This is what is formed at the end of the day. So this is the product. There, where are the reactants? These are the reactants. So we have 2 moles of this. We have 2 moles of this product here, and 2 moles of this reactant 1, and 2 reactant 1, and a mole of this reactant 2, which is oxygen. So, which means it's going to be, okay, let's see, it's going to be K equal to XO3 raised to power 2 divided by XO2 raised to power 2 multiplied by oxygen raised to power 1, because the mole of oxygen is 1. Take note of that it is product over reactant. Okay, let's look at an exercise. Now here's a question. Consider the equilibrium for the following reaction. That is a mole of nitrogen gas combining with 3 moles of oxygen to give us ammonia. Now, step 1, identify the product. The product is ammonia, and we have 2 moles of the product. We have 2 moles of the product. Then, here we have 1 mole of reactant 1, 1 mole of reactant 1, and then we have 3 moles of reactant 2, 3 moles of reactant 2. Okay, now we know this. We can easily write the equilibrium constant without getting confused. Remember, the formula says equilibrium constant K, which is the equilibrium expression, equilibrium constant K, to write the equilibrium expression, you see equilibrium constant K is equal to the mole of product, and what's the product here? Concentration of products, which is ammonia. What's the mole? Ammonia raised to power 2, that's it has 2 here, which is raised to power 2, divided by nitrogen, concentration of nitrogen, of course, it's just 1 mole, multiplied by that the concentration of hydrogen, and hydrogen has up to, hydrogen is having a mole of 3. So this is the equilibrium expression for this chemical equation. Okay, let's see if there are options here and see which of them correctly matches this very expression we've just done. Okay. Now, here are the options. Which of them is actually what we just did? Now, looking at everything here, you will discover that option B actually is what we just did. Yes, this is ammonia raised to power 2, that's NH3 raised to power 2 divided by N2 and H raised to power 3. This is the answer to that question. Okay, I believe by now you've understood this. You've understood this simple concept, how to write equilibrium expression for any chemical equation. Equilibrium constant for any chemical equation. All right, this is my parting words for you. Now, you must note this, that equilibrium constant of solid and liquid species are written as Kc. Why that of system involving gaseous are written as Kp. Involving gaseous species, they are written as what? Kp. So take note of that. I recap. Kc is equilibrium constant for equilibrium for all systems involving solid and liquid. Kp is how we write the equilibrium constant for system involving gases. All right, thank you, and I'll see you next time.